For a long time, the incredible power of quantum computing, the kind of power that could design new medicines or completely reshape finance, was really only accessible to a handful of people. But today, we're going to talk about a huge shift that's happening, a shift that's putting the keys to that power in the hands of developers and scientists everywhere. We're talking about a whole new way to program quantum computers.
And to really get why this is such a big deal, you kind of have to look back. Think about the very first classical computers. Programming them meant using punch cards and ridiculously complex machine code. It was a nightmare. Well, early quantum computing was in pretty much the same boat. If you wanted to run a program, you had to manually control the raw hardware signals, the actual microwave pulses zapping the qubits. I mean, it's powerful stuff for sure, but not exactly user-friendly.
So that brings us to the big question, right? How do we bridge that massive gap? How do we take this incredibly powerful but super complicated piece of hardware and turn it into a tool that someone, say a researcher trying to discover a new drug, can actually use to solve a real problem?
All right, so here's our game plan for this explainer. We're going to start by digging into that machine code problem. Then we'll meet the solution, the primitives. After that, we'll check out their massive V2 upgrade, see how they deal with the all-important problem of noise, and then, the fun part, see how they're used to tackle actual problems. And finally, we'll wrap up by looking at what this all means for the new era of quantum utility.
Okay, first things first. Let's really nail down the core challenge here. For the longest time, if you wanted to program a quantum computer, you had to get your hands dirty with the hardware itself. And this era of direct control, well, it was a major bottleneck for the whole field. The old way of doing things revolved around a command called backend.run, and it basically put all the work on the user. You had to figure out everything, how to translate your perfect, abstract algorithm into something the hardware could actually understand. Then you had to run it, and then you got back this raw data that you had to somehow make sense of. It was literally like being told to build the car engine from scratch every single time you wanted to drive to the grocery store.
So yeah, that build-the-engine-yourself approach just wasn't sustainable. It was holding everything back. And that brings us to the solution. A new, much smarter way to talk to the quantum hardware. So let's meet the primitives.
So, it turns out, when you look at all these incredibly complex quantum algorithms, most of them boil down to one of two fundamental jobs. First up, you've got the sampler. Its whole purpose is to run a circuit over and over and tell you the most likely outcomes. Think of it like trying to find the best route for 1,000 delivery trucks. Then you have the estimator. Its job is to calculate a single, very specific number, like the precise ground state energy of a molecule. And with these two primitives, developers finally have a clean, straightforward way to work.
But, the story doesn't stop there. Having these two tools was a huge leap forward, but the team behind them knew they could do even better. So these primitives just got a massive upgrade, a version 2, that added a whole new layer of power and flexibility.
This V2 upgrade was really a shift in thinking, from just, let's get this to run, to, let's run this as efficiently as humanly possible. It introduced some total game changers. You can now package your work way more efficiently with something called pubs. You can run tons of different versions of a circuit all at the same time. It's like running a whole suite of experiments in one shot. And for the power users who want total control, you can get the raw data back to slice and dice however you see fit.
Now, with all this new power comes a new responsibility. To unlock this incredible efficiency, you, the user, have to make sure your quantum circuits are what's called ISA compliant. All that means is that they have to be perfectly tailored to the specific hardware you're running them on.
So what does that actually mean? Well, it sounds technical, but it really just boils down to 3 simple rules. First, your circuit can only use the real, physical qubits that actually exist on the chip, no imaginary ones. Second, it has to speak the hardware's native language, using only the gate operations it's built to understand. And third, you can only do operations between qubits that are physically wired together on the chip.
Okay, I know what you're thinking. That sounds complicated. But here is the absolute magic of the system. Qiskit gives you a tool called the transpiler that does all of this for you, automatically. It's this amazing pipeline that takes your abstract circuit, maps it to the physical qubits, adds any gates needed to handle the wiring, translates everything into machine language, and even cleans it up to reduce errors. It's the essential bridge that takes your idea and turns it into something that can actually run.
So, now we have a way to translate our ideas into efficient, hardware-ready code. Awesome. But there's another giant elephant in the room we have to deal with: noise. Today's quantum computers are unbelievably sensitive, and errors are just a fact of life. So, what do we do about it?
Well, the primitives come at this with a two-pronged attack. The first strategy is error suppression. This is all about preventing errors from happening in the first place. Think of it like putting up a shield to protect the calculation while it's running. The second strategy is error mitigation. This happens after the run is over. It uses some really clever classical computing to look at the messy, noisy results and figure out what the perfect, noise-free answer probably would have been.
And there are some really cool techniques built right in. For example, there's dynamical decoupling, a suppression trick that keeps idle qubits from just losing their quantumness. But my favorite is on the mitigation side, a technique called zero-noise extrapolation. This one is so clever. It intentionally runs the circuit with more noise just to see how bad the error gets. Then it works backward to calculate what the result would have been with zero noise. It's brilliant.
Now, to make all this super easy for users, these techniques are all bundled into simple resilience levels. You just pick one. Level 0 gets you the raw, noisy data, no frills. Level 1 adds some basic error mitigation, and Level 2 brings in the heavy hitters like ZNE. The key thing to remember, though, is the trade-off. Higher resilience gets you a much more accurate answer, but it's going to cost you more in quantum computer time. You get to choose. Okay, so we've got these powerful, smart, noise-resilient tools that connect our big ideas to the actual hardware. Now for the really exciting part. How are people actually using this stuff to solve real-world problems? First, you've got to decide how you want to run your program. There are three main modes. Job mode is what you'd use for a quick one-off test. Batch mode is your go-to when you have a whole bunch of independent things to run and you want to do it efficiently. And then there's session mode. This is the most powerful. It gives you exclusive, dedicated access to the hardware, which is perfect for those complex algorithms where the result of one run feeds directly into the next. Let's look at a real application, like simulating molecules with an algorithm called VQE. This is where the estimator is the star of the show. You start by defining your molecule. Then you build a flexible quantum circuit for it. Then you hand it to the estimator, which calculates the molecule's energy. A regular classical computer then looks at that result, tweaks the circuit a little bit, and you do it all over again. You just keep looping over and over until you zero in on the lowest possible energy, the true ground state of that molecule. And another huge application is in optimization, using an algorithm called QAOA. This time, the sampler is the hero. You take your problem, say optimizing a logistics network, and you map it onto a quantum circuit. Then, you let the sampler do its thing. Its job is just to find the most probable results. That most common answer it spits back, that's your optimal solution. It's an incredibly powerful way to solve these kinds of needle-in-a-haystack problems. So, let's just step back for a second. We've gone from this world of low-level, super manual hardware control to a powerful, easy-to-use interface with error correction baked right in. So what does this huge shift toward primitives really mean for the future of computing?
I think this quote just says it all, perfectly. The primitives aren't just another programming tool. They're a critical layer of abstraction. They hide all the insane complexity of the hardware, which frees up the chemists, the financial analysts, and the AI researchers to focus on what they do best, solving the world's hardest problems without needing a PhD in quantum physics to do it. And this brings us right to the final, and honestly the most exciting question of all. We are officially stepping into the era of quantum utility, the time when these machines are finally becoming useful for real-world advantage. So now that the tools are in the hands of the innovators, the question isn't if we'll see breakthroughs, it's where will we see them first. Is it going to be in designing new drugs, optimizing global supply chains, or creating entirely new financial instruments? That is the incredible future that these primitives have finally unlocked.